Power factor is a topic that we touched on in a number of the previous videos I did about alternating current, but we only just touched on it because I didn't want to take any of those videos too far off topic. Well, this video is all about power factor. And what is power factor? Well, you might have seen it on some of those inexpensive AC power meters you can buy for home use, and they usually have a display showing exactly that, and it's usually a number between 0 and 1. And what is that number? Well, in a nutshell, it's how much of the current that is being delivered to your device is actually providing real power to the load. And that might seem a little bit mysterious, so let's take a look at what it actually is. On the video about reactive power, I drew these graphs. This is a graph representing reactive power where the current in this purplish reddish color is out of phase by 90 degrees from the voltage, and that's what we would typically get for something like an inductor, or out of phase in the other direction for a capacitor. And when the voltage and current are out of phase, what we found out is that even though there was current flowing that you could measure with an ammeter, there was no net power flow, because if you multiplied voltage and current together on a pointwise basis, what we could see is during this part of the cycle, we had positive power flow from the source into the load, but then the next part of the cycle, we had the same amount of power coming back. So for a reactive device like an inductor, we have the current going back and forth and carrying the power back and forth. So there is no net power flow. We call that reactive power. Real power is when the voltage and the current are in phase. You'd get that from something like a resistor. And if we multiply them on a pointwise basis, what you can see is there is a pulse of power at the peak of each of the voltages on an AC cycle. So we have a burst of power going into the load, then it goes down to 0, then it goes back up to another peak, and we get these pulses as you might expect. And many things are indeed a combination of these two waveforms where they add to get a current that is somewhere between in phase 0 degrees and out of phase 90 degrees. And that's what you might get with an inductor that has a certain amount of resistance in it, or an inductor that's part of an induction motor and the resistance is indeed the load that the motor is driving. Well, how do we handle that? We handle that by something called power factor, and it's really how much of the total current that you would measure with an ammeter is the current that's contributing to real power. And let me show you very quickly how we get that. So to look at power factor, I'm going to draw a nice little graph here like this. And this axis we're going to call 0 degrees. It's going to represent the real power, or the current that is in phase with the voltage. And then over here we will have the 90 degree axis. It will represent the reactive power, the reactive current that is 90 degrees out of phase with the voltage. And to represent any current we want, we'll draw the current on here like this with an arrow, and the length of this thing will be the current in amps, or could also be the power in volt amps. And the angle here is the phase angle of the current. So if we had a resistive load, this arrow would be down here, the phase angle would be 0, all the current would be a real current or in phase current. If we had a reactive load like a perfect inductor, maybe a superconductor inductor, this arrow would be all the way up here, and the angle would be 90 degrees. We'd have no in-phase current. We'd only have reactive current. So what might be of interest would be, how do we, if we have the total current, and this current you could measure with an ammeter if you just put it on a wire, how can we tell how much of that current is indeed the real part, the part that's delivering real power? And you might be looking at this and saying, wow, that forms a triangle with an angle. And if you remember high school trigonometry, which nobody does, and most people, if they do remember, try and forget, well, the real part down here is equal to, we'll call this R, by the way, and I'm going to call this total current T, for lack of a better term. Well, we can say R equals T times the cosine of theta. So the cosine of theta, the cosine of that angle, simply tells us what fraction of the total current is in-phase current. And it also tells us what fraction of the apparent power, in other words, the current times the voltage, not worrying about the phase, is the real power, the power that's delivering energy to the load itself. And so we can give those things names. We usually call the apparent power, the, if you want, total power, real plus reactive, we usually call it S for some reason. And we also tend to call the real power P, power. So maybe I should sort of make a note here. This is current. Down here, we'll do it with power. So we're going to say the power P, the real power, is equal to the apparent power, S, times cosine of theta. And we call this cosine of theta the power factor. So we can say P equals the apparent power times the power factor. And the power factor is typically a number between 0 and 1. If it's 1, it means the angle is 0 degrees. Everything is in phase. All the power is real power. So the length of the apparent power and the real power is the same. If we had a capacitor in there and we now had everything out of phase and there was no real power, the power factor would be 0. So it's really just a measure of how much useful power we're delivering from the total power or total current flowing through the power lines. Obviously, we would like the power factor to be as close to 1 as possible. In the old days, with nice, simple inductive loads and sometimes even capacitive loads, well, that was fairly easy to achieve by adding capacitors and inductors. But today we have a much worse situation with electronic power supplies where this nice simple relationship is completely messed up. So for electronic power supplies, well, let's look at the simplest, worst type of input stage for an electronic power supply. And that is something like this. Here's our AC input, a nice sine wave. This device is a diode. It only lets current flow in one direction. And this is a capacitor. This is what can be used to store energy for a short period of time. And that's how we go from AC to DC, because this diode only lets current flow in one direction. That creates direct current, hence the name. And well, let's see what happens if we apply AC to this. we'll just draw a nice little graph. Here is our AC input voltage, like that. And, well, it starts off, the capacitor has no volts on it. We apply the AC, and we'll assume we turned it on when the cycle was at 0 just to make things look kind of nice. Well, as the voltage on the applied AC goes up, the voltage on the capacitor goes up. The capacitor charges, and it goes up and up and up till we get to the top here, and maybe we'll just pretend the top is 100 volts just to make our lives easy. When it gets to 100 volts, well, the applied AC starts going down, so now the voltage on the capacitor is higher than the voltage here. The voltage here now might be 99 volts. Well, the current would want to flow in this direction. The diode stops it, so the current just stops like that. And we still have 100 volts on our capacitor. Well, what happens over here? Well, nothing flows. The voltage goes negative. Well, again, this is more positive than that, so nothing flows. So nothing happens along here. Now we get the next positive part of the AC cycle. Well, let's imagine that the voltage on our capacitor has dropped to 99 volts because something has been using some of the DC energy stored in it. Well, as the AC voltage goes up, right now it's like 10 volts, 20 volts, 30 volts. That's less than 99 volts. Nothing can flow through the diode. However, when we get up to 99 volts here, well, suddenly we can start getting current flowing, and it'll flow till we've charged the capacitor back up to 100 volts, and then just like before, it will stop. And we would get a pulse like this at every subsequent peak of the AC cycle. So that doesn't really look like a sine wave to me. Now, in most cases, we would use here what's known as a full wave bridge. What that would do is allow the negative part of the cycle to also charge the capacitor, and indeed what we would expect to see is a pulse just like that one down here. So in the end, what we would see going into our electronic power supply, I'm just going to draw our AC again, not necessarily at the same frequency as that one. We would see sharp pulses of current going in only where the AC cycle peaks. And that's really quite horrible for the power system. And the reason it's horrible is it doesn't look like a sine wave. And indeed, what this is a waveform that has energy at the sine wave. So believe it or not, in here there is a certain amount of 60 hertz, well, in North America, but there's also energy at all the harmonics. So at 120 hertz, 180 hertz, and so forth. The harmonics are the multiples of the fundamental frequency. So 2 times 60, 3 times 60, 4 times 60. And I'm going to just show you how the harmonics can make up these jagged pulses. And I'll do that just by drawing a very simple example with the fundamental and the third harmonic. So I'm going to try and draw a nicely formed AC waveform here. So that's our fundamental at 60 hertz. And what I'm going to try and do is draw another waveform, the third harmonic, so that would be 180 hertz. And I'm going to draw it like this. So let's imagine that the power supply is drawing a certain amount of current at 60 hertz and a certain amount of current at 180 hertz. Well, those two currents add, so we can sort of see what's happening. Well, this is actually a negative current, so it's going to suppress this a bit. So we'll sort of say up till here, this is sort of suppressed down, but it's going up faster than this is. So maybe it does something like this. Up here, the third harmonic adds to the fundamental. So makes it go up like that. Down here, they cancel. We get something like this. And if we carry that through, we get a waveform that looks something like this. So not as jagged as this one, but you can see it's now quite peaky. Well, it turns out if we start adding higher and higher harmonics, this gets narrower and narrower and more jagged, and indeed we end up with something resembling that. And it turns out when you have peaks like this, you indeed have energy or current, if you want, at all of those higher harmonics. That's a huge problem for the power system, because things like transformers and generators are designed to operate at the fundamental frequency of 60 hertz or 50 hertz in most other parts of the world. And when you start getting currents flowing at higher frequencies, bad things happen. For instance, in three-phase transformers, normally the neutral currents all cancel or get very close to canceling. Well, the harmonics at certain frequencies cause those neutral currents to add, and so you get huge neutral currents flowing. You also, in some transformer configurations, get circulating currents flowing. So it's a real problem. The power company does not like it when we have devices using current in spikes of that nature. And this is also something that is included in the whole power factor thing, but it's really much harder to characterize because, as we're going to shortly see, the shapes of these pulses and stuff can vary quite a bit. The power company requires people to try and prevent these spikes. It's kind of hard to characterize how bad they are. Maybe the best way of doing it that I've seen is to do something like compare the energy in the fundamental frequency with the energy in all the harmonics, and that could be considered something like a power factor for these spiky type power supplies. So, enough of theory. Let's look at some real things, and you're going to be astonished how terrible some of these currents actually are. So to look at power factor on the scope, I have this box that I built a while ago hooked into the circuit, and what it does is it gives us a measure of the line voltage going onto one channel of the scope, and it gives us a measure of the current converted into voltage going into the other channel on the scope, the lower channel. And the way I have it set up right now is that 1 milliamp of current coming from the load corresponds to 1 volt on the scope dial, or for that matter, 1 volt on the voltmeter that I've set up here. So right now it's showing 0.48 of a volt. That means about 0.48 or 0.5 of a milliamp of current is flowing into our current sensing box, and it's coming from this quick test device, which we're going to connect all our loads to. And you might be wondering, well, why is the quick test consuming about half a milliamp? Well, it has a nice little neon bulb, and I can turn up the scale on the scope a bit, and we can rather nicely see the current pulses going through the neon bulb. The current only starts when the voltage on the neon is probably somewhere around 90 volts. It very quickly comes to a peak and then eventually falls off to, well, 0, and then the thing repeats at the positive and negative cycles of the AC. So it won't really affect us because in most cases the current of whatever we're testing is going to be significantly higher than the current from the neon bulb. So the first thing we will test is this group of capacitors that we used in our previous video for the tuned circuit, and I have it just hooked up with these little test leads to the quick test. And what we'll do is close the quick test And there you go. You can see the current through the capacitor rather nicely. And if we look at its peak, it certainly precedes the peak of the AC voltage by about 90 degrees, which is exactly what we would expect. And as before, the waveform of the current through the capacitor is indeed quite messy, and that's because the capacitor is essentially emphasizing every slight difference in voltage along the input AC waveform. Even if we can't see it, it's bringing it out and causing these distortions, but it's actually pretty nice, and compared to what we saw the other day, really nice. So that's the capacitor by itself. Oh, and we can look here and see there's about 2.6 milliamps of current flowing through the system, so it's not really very much. Okay, so I will disconnect our test leads, and now I will hook the test leads to the toroid, the transformer, and we'll see what we get through it. Well, we get a somewhat nicer waveform, and if we compare it to the incoming AC waveform, well, it is lagging the AC waveform. It's not lagging by a full 90 degrees, and that's because there's a fair amount of resistive or mimicking resistive losses in the core, which adds a real current. So it's probably lagging by about 45 degrees or something like that, as opposed to the full 90. Okay, and finally, let's take a look at what happens when we have the inductor and capacitors in series. So they essentially cancel their leading and lagging waveforms. Well, here you go. We can bring that one up, the current one, this current one, we'll bring it up so we can compare it with the AC input, and sure enough, they're pretty close. We haven't succeeded in completely making them in phase because those capacitors are all of a limited size, 0.01 microfarads, and I was adjusting it by adding more or less of them. This was as close as I could get, and it's very close. So this would actually be very close to a power factor of 1 because those waveforms line up so nicely. Whereas when we only had the capacitor, it was probably more like a power factor of a 0 because it was pretty much at 90 degrees. And when we had just the inductor, it was probably a power factor of around a half or so. All right, so that is the stuff we looked at last time. Now what I'm going to do is disconnect this, and I'm going to change this box to a different current measuring box that is set up to measure currents more in the amp range. So we'll start by testing a 40-watt incandescent bulb, which should have a perfectly in-phase current and a power factor of essentially 1 because it's very close to a resistor. And here we go. There's the current. We can see it quite nicely, and we can look at our voltmeter and see in this case the voltage maps directly to current. So we have about 0.32 amps flowing through the light bulb. That's what we'd expect for a 40-watt bulb. This is the type of bulb you get in an oven or a refrigerator. And yes, you can certainly see these things line up quite nicely, a power factor of 1. Do you think we're going to see anything that good again? Probably not. All right, let's look at some different light bulbs, and maybe we'll start with a really old one. This is one of the first compact fluorescents, probably from 30 years ago, made by Osram in the United States. They don't make them in North America anymore. And wow, look at that jaggy spike there. I'll just bring it down a bit, or maybe I'll bring it up. a bit so we can see it. How's that? So all the current is being drawn in these spikes over here. We're seeing an average current of about 1/4 of an amp, according to the voltmeter. I'm not sure how much I trust this because these spikes are so narrow. The accuracy of the voltmeter will depend on how many times the voltmeter samples the voltage along here, and you could certainly see it not getting the spike properly or only sampled at a few positions to get an average type current. So I'm not 100% sure. For what it's worth, you can't see it, but off screen I have this whole setup plugged into the power meter we previously used. It's recording about 0.21 amps current. So clearly the two digital devices are somehow averaging or getting an RMS value of this current quite differently. Probably one or both are doing it improperly. So that's not untypical for a very simple electronic power supply, where as the voltage goes up, you suddenly have it going through a diode and charging up a capacitor, and when the capacitor is full, well, the current drops again. Absolutely terrible for the power grid, because this has all sorts of harmonics, probably going up well beyond the 10th or 20th harmonic. It's so spiky. So that's a really bad waveform if you're trying to supply power. Okay, that was the oldest compact fluorescent I have. Here's a newer one, and they came along with these twisted ones. There we go. And we've got somewhere around 0.33 amps, and once again, maybe we'll bring this down a bit. You can see that we have another very spiky waveform, and you can also probably see the current changing a bit as this bulb heats up. These bulbs are actually designed to, not the best connection there. These bulbs are designed to operate best when they're hot. It all has to do with the pressures of the gases in there and the amount of mercury inside the fluorescent tube that gets vaporized. Now it's getting really bright, probably drawing a bit more current. I'm going to remove it because I'm getting blinded. Have you ever seen one of these? This is the Circulite. It was made by GE. I think they started making them in the 60s. I remember my granny had one in her kitchen when I was a little kid. And when compact fluorescents came along, they started making these fixtures. It was a very quick way for GE to get into the business of compact fluorescents. So, well, let's hook it in and see what its current looks like. That flicker is very typical, but look at that. The waveform, while not a perfect sine wave, it's a little bit more triangular, so it has some harmonics, but it's basically very nice. It's lagging the AC voltage a bit. The current is lagging. What does that mean? It means it looks like there's an inductor in there, and indeed there is. The way these bulbs work is they essentially have a big inductor in series with the bulb to limit the current going through the tube, and that's because all these gas discharge tubes actually have a negative resistance characteristics, and if you hook them into the AC power directly, well, they burn up real quickly. So you use something like an inductor to limit the current. So that's what's happening. And I mean, the power company would be so happy if everything produced current waveforms like this, because yeah, a bit of harmonics, but a very nice waveform. So, okay, that's the Circulite. I have a selection of bulbs that I just pulled from various places in the house. That's quite typical. This is a Noma bulb, and you can see, like we'd seen before, a very classic charging of a capacitor in a very simple electronic power supply producing really large spikes. And, you know, the real problem is even though this bulb in theory is only consuming about 1/10 of an amp or so, well, these spikes are really high. They're probably in the amp type magnitude, probably about the same as a 100-watt light bulb. So when this spike is at its peak, it's drawing the same current as a 100-watt light bulb, and for that instant there's about the same amount of power being lost in all the power lines and power system for that 1 amp current being drawn. So not very good, and again plaguing the power system with horrible harmonics. Here's a little floodlight. It's also NOMA. And look at that. I think it's maybe newer. The shape of the current is completely different. And what I can imagine here is they've done some sort of a correction in the power supply to make the current drawn into a much wider pulse. And you can see that it is really, you know, getting to resemble a sine wave other than these two things. So, you know, a few harmonics, but the power system would probably be quite happy with that. Here's sort of a bathroom spotlight type bulb. Look at that really strange current. Again, probably intentionally spread out using some circuit or another to try and make it better than those very simple, very peaky waveforms. This is one of those fancy, will look like an old incandescent bulb type things. And I wanted you to see this. Look at that strange waveform. Nothing. It suddenly goes up, then it draws a constant current, and then it goes down again. I've never seen anything like it. I can't imagine what the design of the power supply in there might be like. Certainly probably better than those very narrowly spiked ones, but not that great. So who knows what they're trying to achieve. Here's one I picked up on clearance at Home Depot, and terribly spiky again. So this is a very simple power supply in contrast to the previous one. What else do we have? Oh yes, maybe the best bulb for last. So this bulb is an incandescent bulb, and it's advertised as a bulb that starts off bright and then gets dim as you fall asleep, probably for a kid's room. And of course we all know that that's important because there are monsters that live under the bed and come out when it's dark so you can't fall asleep. Well, if we plug this bulb in, you see a characteristic where you get a nice sine wave, except that it sort of takes a while and only then turns on, and then the sine wave completes, goes down to 0, and then again takes a certain period before the thing turns on. That's very typical of the old style lamp dimmer. There would be a triac inside the bulb with some sort of a timer circuit, and the more it delays the current being turned on, the dimmer the bulb will get. So over time we would see the delay of the bulb turning on to progress more and more through that cycle. So there would be some harmonics, high frequency components in there because of this, but it certainly wouldn't be nearly as bad as many of the other things we looked at. Okay, a couple of other things to look at. The fluorescent lamp over my lab bench, and it's not really fluorescent, it has LED replacement bulbs in it. How good or bad are they? Well, we saw something like this before in one of the other bulbs. I don't remember which, but clearly some sort of circuit in there that's trying to spread out the middle current pulse to make it resemble a sine wave considerably better than those very peaky ones and reduce the harmonics. So they've done a good job. And I have my great big isolation transformer. This is a kilowatt type transformer. And if we plug it in here, what do we get? Well, we get, and we've seen this in previous videos, a waveform that shows when we get close to the peak of the current because of saturation in the core, and we're moving up the BH curve. As it gets more saturated, we need more and more current to achieve the required magnetic field, so we get these peaks. So something like this does produce some harmonic. It's not as jagged as some of those electronic power supplies, but it certainly will not be ideal for the power system. Now, this isn't as bad as it looks, because if we look here, the current, the RMS current here, is about an amp. Well, for a 1 kilowatt transformer at 120 volts or so, we would expect 8, 9, 10 amps flowing under full load. So this really would be pretty much disappeared under the situation where the transformer is really designed to be operated. So it's not that much of a problem. Finally, I have here this little transformer. This was a transformer that we used in our back-to-back transformer video, and people were wondering about the current through it. So we're going to find out. What are we getting? We're not getting much, about 33 milliamps. And I actually remember this transformer was drawing around 30 milliamps, so that makes sense. And once again, we see that same characteristic of a magnetic core beginning to get up to the top of the saturation curve at the peak of the current. And just as I said about the other one, if this thing was under full load, we would probably have 10 times the current flowing in this peak, and so you'd hardly notice it at all. So, one more thing to test, and that is my nice old Dell Latitude laptop. And I got this laptop here for testing because I was thinking I'd like to show you a computer power supply, but I didn't want to hook up my nice desktop computer to it, and I've just plugged it in. The power supply is connected to the laptop. The laptop is not turned on, and what you can see on the current is a very peaky current, just like we've seen for some of the more lousy light bulbs. The current itself is only 20 milliamps, and that's because the power supply is operating in some sort of a low power standby mode. Now, I'm going to go turn on the laptop, and what we'll do is see what happens to the current and the waveform over here. Okay, I'm turning on the laptop now. So it should start its boot process, and you can already see the current changing. And indeed, the current has gone way up. So I'm bringing the trace on the scope more in line to something we can see. The current is now about half an amp, according to the voltmeter acting as an ammeter. And you can see they've, just like some of the better lamps, done a few things to try and make the current resemble a sine wave a bit better. And I guess as the thing occasionally uses less and less power, it goes back into that power saving mode. But when it's operating and it's drawing different amounts of power, you can see how the waveform changes a bit. And of course, that's the difficulty of a computer power supply, because it's having to adjust to the amount of power that the computer is using at different times. So that's what a probably 15-year-old power supply from a very good computer looks like. You would expect modern ones to be like that or even better. And finally, let's look at the current through the grinder, which I used a while back as an induction motor example. And in the case of the grinder, it's really an unloaded induction motor. I've hopefully got the grinder already turned on. And I'm even going to turn this current down a bit because it'll probably draw a lot, drop to 6 amps on startup. And it does. So you can see it's drawing a very nice current. As it comes up to speed, the current goes way down. Interestingly enough, it's more like a triangle wave, and what that probably means is there's a certain amount of saturation occurring in the core, but at the same time, because the core, in the case of an induction motor, contains a significant air gap, the saturation isn't nearly as prominent. And you can see the delay in the current from the voltage. Again, typical of an inductor, but it's not quite a full 90 degrees because the grinder is not very loaded. In fact, it's just overcoming the friction. But what I'm going to do, just so we can see it, is push something against the grinding wheel, and we should see what happens to this waveform. Okay, here goes. Let's repeat that with the current turned way down. You'll notice that as the grinder gets more and more loaded, the current waveform gets larger, the current goes up, but more importantly, it also shifts position, getting more and more in line with the voltage waveform, so the power factor gets closer and closer to 1. And that's exactly what we would expect from a heavily loaded induction motor. Well, I hope you found this as interesting as I did. I was certainly amazed at how varied the current waveforms were for all those different electronic power supplies, and indeed how bad some of them were and how good other ones were. And you can certainly see what a problem this is for the power companies, and it's a problem that's only going to get worse and worse in the future as more and more things have electronic power supplies. If you do have any questions or comments or thoughts, please put them in the comments below or send me an email. And if you did enjoy the video, please consider subscribing or liking. It really helps a small channel like this one. And see you next time.